So remember that I said that not all energy is never gained or lost. That's the principle of conservation of energy, but it's simply transferred between stores. Now, when it's transferred between stores, though, we do waste some energy. We don't lose it, but it gets wasted, all right? And so the idea is that when we talk about energy efficiency, we're saying how much of the energy, when it's being transferred, is being transferred into a useful form, which is the form that we want it to be in, all right? So for example, for a light bulb, okay, the useful energy output of a light bulb is light. That is the purpose of a light bulb, right? But you also, if you've ever touched a light, especially a filament lamp, but even the new energy saving LED ones, right? The idea is that they put out light, but they also get warm. Well, the warmth, that's a wasted energy output. The point of a light bulb is not to give off warmth. That's the job of a heater. Okay, but if you think about a heater, okay, so useful energy is heat, but some heaters also have, if you think about like they have an element that glows. That light is actually a form of wasted energy for the heater. So when we talk about wasted versus useful energy output, it's really about what is the purpose of this appliance or thing that you are doing, all right? And so the formula for energy efficiency is straightforward, all right? So the idea is that it's the useful energy output. So this is the idea of how much energy is being actually transferred into the form that you want, the useful energy output divided by the total energy input. Now, usually we talk about this as a percent. So if you want it as a percent, then you would multiply this by 100. That's it. That's the energy efficiency equation. All right. And so obviously, the more useful energy output you have, the more efficient your appliance or whatever it is will be. Now, along with the energy efficiency formula, you need to be able to draw a Sankey energy diagram. And this is one that a lot of students seem to struggle with. So I'm going to try to walk you through it here and see if it makes any more sense this way around. Okay, so a Sankey energy diagram, what this is it's a visual representation of transfer of energy. And the idea is that it is proportional. All right. And so the visual representation of the energy transfer, which means that it's literally you're starting with one type of energy, you're going to another. How much of that energy of the energy that you're transferring is actually being used for what it wants to be used for? All right. So I'm going to give the example of a kettle. All right. Let me get some things written down, and I'll be back. So a kettle receives 1,000 joules of electrical energy. All right, that's the energy input is 1,000 joules. 600 joules of this heats the water, so that's the useful output. That's the purpose of a kettle, right, is to heat water. That's what you want that kettle to do. So this is your useful energy output, right? The 1,000 joules, so it's receiving it, right? This is what it starts with. This is 1,000 joules, so this is your energy input. Your total energy input. Okay, so what you can see is that, so if I were to talk about the efficiency of this, right, I'd have 1,000 joules as the total energy input, 600 joules is the useful, so 600 divided by 1,000 times 100 would give you a 60% efficiency, all right? Now, 400 joules heats the kettle itself, the metal part of the kettle, and the air. Well, that is wasted energy. That's not what we want the kettle to do. We don't care whether it heats the air, all right? And so this is a wasted energy output. It's really important that you understand the numbers that you're being given before you start to draw your Sankey energy diagram. All right, now I'm going to keep this here while I actually draw the energy diagram here because I'm going to do it legitimately. Crazy me. All right, so let's say, so we have 1,000 joules. All right, now the idea is that I'm going to draw a big arrow, and the arrow will have two heads. It's always going from left to right, and the arrow head pointing forward is going to be the useful energy, and the arrowhead going down is the wasted energy. That's not the energy that is of use to us. All right, and I said it has to be proportional, so you can decide, all right, how big you want your your arrow to be. The length of it doesn't matter. What matters is the height of it, all right? So it doesn't matter how long you make it. It's all about the height. This is the key part, all right? I'm going to make mine 10 centimeters because it's 1,000 joules, and that makes makes the math really easy, all right? So there's my 10. I draw it here, all right? I have 10 centimeters now. So this is the back end of the arrow. And I'm going to draw just a little bit here. Like I said, the length doesn't matter. I'm just going to try to make sure it's straight. All right. Make sure it's straight again. There we go. Okay, so this is the beginning of my arrow. Make this one a little bit longer here. Now, and then I can label this if I want. This is the energy input. The idea is it's an arrow, so it's showing you the transfer from one type of energy to another. So if I wanted, I could label this total energy input. And I would also, preferably, you would label it also with the value and the type of energy. So we know that this is electrical energy, okay? And it's 1,000 joules. So there, I've got my total. So that's the first label you need. You always need 3 labels on this. So the total energy oh Lord, total energy input. Sorry, guys. Total energy input is 1,000. I'm not going to redo the video for that. Sorry. The total energy input, all right, and it's 1,000 joules, it's electrical. Now, we know that 600 joules heats the water. That's the useful. Now, this whole thing is 10 centimeters, or hypothetically should be still on this side. Yes, it is, all right? So it's 10 centimeters. So 600 joules, if 10 centimeters is 1,000 joules, then 600 joules is going to be 6 centimeters. Hope everybody sees that. All right, I've got this marked as 10. So from 10 down to 4, that's where I'm going to draw separation. This separation needs to go somewhere in the middle of the arrow. Don't draw it all the way. Don't trace it all the way back. That's not right. Okay. Now, so that means that these 6 centimeters here, this represents the 600 joules. So I'm going to do a big arrow here. Okay. And this is my useful energy output. And then the rest, the other 4 centimeters, that represents the 400 joules, that's waste. So that's going to get pointed down. So this is your Sankey energy diagram. It always has at least 2 arrows, usually just 2 arrows, okay? And the back of it is the total energy input, and these represent the energy output. So the arrow going forward, this is the useful energy output. And this is the wasted energy output. This would be the minimum label that you would need, but if you have the information, it's usually a good idea to include, again, the values and the type. All right, so the useful energy output we know is 600 joules, and if it's heating things up, right, it heats the water, so what type of energy is that? That's going to be thermal. And the wasted energy output is 400 joules, and it's heating the air and the kettle. So it's still heating things, so that's still going to be thermal. So that is your Sankey energy diagram of this kettle. All right, it's always going to have 2 arrowheads, and the key part is that it is proportional here. All right, that this is the same, right? These 2 add up to the total energy input because, again, you're not losing or gaining any energy overall. You're simply transferring it. And so the idea is that this split on the arrows has to be proportional to the values that you are given. Right, so this, I'll write it out. This is 4 centimeters, and this is 6 centimeters up here because this represents the 600 joules and this represents the 400 joules. By the way, once I go down, it doesn't matter whether I keep the same proportion or not. It's all about the proportion at the point where the arrows are separated. So if this arrow gets a little smaller as it points downwards, that's not a problem. That's okay.